Gauss'Law, cylindrical symmetry. We have a very long rod with charge density lambda, uniform distributed. To find electric field around an infinitely long plastic draw with a uniform positive linear charge density lambda, we will find E around it. Okay. Now, we try to make a Gaussian surface, so we can use this one. In this case, we have cylindrical symmetry. Okay. For example, we want to find the E around it. A distance that's point to this rod is R. And we can imagine this E should along the radius R by symmetry reason, right? Now, we want to find this dot line. Any point on this dot line will have the same E as this point by symmetry reason. Okay? Yeah. And also, we make a round. Any point around on this circle will have the same magnitude of E along the radius R. A direction different, but the magnitude is same. So finally, take advantage of the cylindrical symmetry. We'll make a Gauss surface as a cylinder, okay, with radius R, because this is R, okay, and top surface and bottom surface are perpendicular to this line, to this rod, okay. Now, we try to use the Gauss law in this cylindrical symmetry situation. We have three surfaces on this closed Gaussian surface. Okay. First, okay, is top one. Okay. Second is side one. Third is bottom one. On the top, you see the E is perpendicular to the rod, should be on the surface, and dA should perpendicular to the surface. So this E dot dA perpendicular, the integration equal to 0. This is dA, this is E, so they're perpendicular. This is 0. And on side surface, E is along the radius. dA is outwards and perpendicular to the one, so along the radius too. So E dot dA equal to EdA. EdA. And E, by symmetry reason, on this cylinder surface would have the same magnitude. So E parallel to dA and E is constant, so you get E take it out, you get EA. Okay, EA. The bottom surface at the same reason, okay, bottom surface, okay, is equal to 0 because dA is downward, perpendicular to the area. E is along the radius, so it's equal to 0. So this integration on the left side equal to integral EdA. E is constant, so it becomes EA. This A is the area of side surface. Okay, and we see this side surface equal to 2 pi r h, right? 2 pi r h. And this Q enclosed is this rod inside the surface, so it will h lambda, h lambda. We cancel out h on both sides, and we get E. This E is not uniform. The smaller the E, R, the larger the E, okay? And this is the one. We got it. Yeah. The lambda is the linear charge density of this rod. Sample. Upward streamer in the lightning smoke. This is the upward streamer. Okay. The woman in the picture was standing on the lookout platform in a national park when a large storm cloud moved overhead. Some of the conducting electrons in her body were driven into the ground by the cloud's negatively charged base, leaving positive charge. Okay, this lady is positive charged. Okay, she was highly charged because her hair stands repel one another and extend away from her along the electric field line produced by the charge on her. Lightning did not strike the woman, but she was in extreme danger because that electric field was on the verge of causing electric breakdown in the surrounding air. Such breakdown would have occurred along the path extending away from her in what is called an upward streamer. The upward streamer is dangerous because the resulting ionization of molecules in the air suddenly frees a tremendous number of electrons from those molecules. Had the woman in the figure developed an upward streamer, suppose the free electron in the air would have moved to neutralize her because it's positive. The free electron would move neutralize, producing a large, perhaps a fatal charge flow through her body. That charge flow is dangerous because it could have interfered with or even stopped her breathing and the standing beating of her heart. The charge flow could also cause birth. Now let's model her body as a narrow vertical cylinder of height L 1.8 meter and radius 0.10 meter. Assuming that charge Q was uniformly distributed along the cylinder and that electric breakdown would have occurred if the electric field magnitude along her body had exceeded the critical value E critical 2.4 million Newton per Coulomb. What value of Q would have put the air along her body on the verge of breakdown? Now, this is a very vividly, okay, like the person, okay. Now, we see, because it's a charge, uniform charge, okay, so this is like a cylinder. It has E is lambda over 2 pi epsilon. See? Okay? And this is depends on the charge, right? Yeah. This R, the larger the R, the smaller E. When you have a breakdown, it must happen smaller R, okay? Small R. And the charge is Q over L. Q is the charge the woman have. L is the head. Okay. So in this case, we found the Q. We put everything inside. Very simple, straightforward. Okay. This R is 0.10. Okay, meter. This is meter. Okay. L is 2.4 times 10. You see. Okay. L is 1.8 meter. And E is 2.4 million, 10 to the 6. We get the answer. It doesn't look too much, only 24 microcoulomb, but it's very dangerous. Sample. The visible portion of a lightning strike is preceded by an invisible stage in which a Coulomb electron is extended downward from a cloud to the ground. These electrons come from the cloud and from the air molecule that are ionized within the column. The linear charge density lambda along the column is typically -1 times 10 to the -3 coulomb per meter. Once the column reaches the ground, electrons within it are rapidly dumped to the ground. During the dumping, collisions between the moving electron and the air within the column result in a brilliant flash of light. If air molecule breaks down, ionized in an electric field exceeding 3 times 10 to the 6 Newton per Coulomb, what is the radius of the Coulomb? Now, we look at this one. This is a symmetric symmetry, E equal to lambda of C. What we know the breakdown E. Okay, we want to find the R. We also know the lambda. Okay, so lambda is 1 times 10 to the 3 per meter square. Okay, and we put everything inside. We find the R. This R is about 6 meters. So the diameter is about 12 meters. Light flash during the thunderstorm.